Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is plugging circuits. Our objective is to introduce the concept of plugging a motor and examine ladder logic diagrams facilitating or preventing this action from occurring. This lecture operates under the assumption you have watched the Reversing Motor Starters with Interlocks lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. As you'll recall, we ended the Reversing Motor Starters with Interlocks lecture on a bit of a cliffhanger in that I briefly introduced a reversing motor starter using push-button interlocking and put off a thorough analysis of the ladder logic diagram until another day. That other day is now upon us. This particular reversing motor starter using push-button interlocking exhibits a phenomenon called plugging, where the term plugging means the instantaneous reversal of applied phase sequence while the motor is running. Phase reversal develops a counter torque, and a plugging action can be used to bring a motor to a rapid halt or enable quick reversal of rotational direction. Note this reversing motor starter with push-button interlocking makes use of mechanically interlocked forward and reverse buttons that when one mode is selected, the opposite is deselected. Note the normally closed side of the mechanically interlocked forward push button acts just like a stop push button for the reverse circuit. Similarly, the normally closed side of the mechanically interlocked reverse push button acts just like a stop push button for the forward circuit. Push button interlocking should be used only in conjunction with mechanical and electrical interlocking and is intended to supplement these methods, not replace them. Note this reversing motor starter also includes mechanical and electrical interlocks as well. In the event of a jammed or slow on the draw contact carrier, these methods prevent simultaneous closure of both contactors. Recall that simultaneous closure of both the forward and reverse contactor constitute a dangerous phase-to-phase event to be avoided at all costs. The complementary protection methods ensure this event does not occur. In contrast to reversing motor starters using only mechanical and electrical interlocks, this particular reversing motor starter reverses direction immediately without the stop button being pressed. Allow me to demonstrate. Let's make some room by removing the primary schematic and zooming in on the pilot ladder logic. Next, let's ditch the ugly dashed mechanical interlock between the forward and reverse push buttons. The dashed lines are just going to make our analysis difficult. You're just going to have to remember that they're mechanically interlocked. Note, forward is green, reverse is orange. Consider the following scenario in which an operator presses the forward push button. The normally open side of the mechanically interlocked forward button closes and the normally closed side opens. Via the normally closed e-stop, the normally closed stop, the normally closed side of the reverse button, the now closed forward button, the normally closed R2 electrical interlock contact, and the normally closed overload contact, the F coil of the forward contactor would be energized. When the F coil is energized, its associated contacts change states. The normally open F1 holding contact in parallel with the forward button closes. The normally closed F2 electrical interlock contact opens, and the primary F contactor would close. Referring to our previous primary schematic, note that the applied phase sequence as provided by the forward contactor would be L1, L2, L3. The motor would experience inrush current and begin rotating clockwise. Once the motor reached rated speed, the inrush current would subside and level out at the full load rated current. If an operator were to release the momentary contact forward push button, the spring return would return it to its normally open deactivated state. Note that the now closed F1 holding contact maintains the energized state of the F contactor coil. This means the primary F contactor stays closed and the motor continues spinning in the clockwise direction. That's the point of the holding circuit. It maintains the last asserted state. While traveling in the forward mode, consider what would happen if an operator pressed not the stop button, but rather the reverse button. The normally closed side of the mechanically interlocked reverse button opens, and the normally open side closes. Via the now open normally closed side of the mechanically interlocked reverse button, the forward contactor coil is de-energized, and the associated contacts return to their deactivated state. The normally open F1 holding contact opens, removing the path in parallel to the forward push button. The normally closed F2 electrical interlock closes. The F primary contactor would open. Via the normally closed E-stop, the normally closed stop, the normally closed side of the mechanically interlocked forward push button, the now closed normally open side of the mechanically interlocked reverse button, the normally closed F2 electrical interlock contact, and the normally closed overload contact, the R coil of the reversing contactor would be energized. When the coil of the R contactor energizes, its associated contacts change states. The normally closed R2 electrical interlock opens. The normally open R1 holding contact in parallel with the reverse push button closes, and the primary R contacts would close. Note from our previous primary schematic that the applied phase sequence as provided by the reversing contactor would be L2, L1, L3. Phase sequence has been instantaneously reversed without the need of the stop push button. The motor would experience a substantial current draw, many times greater than that of normal inrush, and would rapidly decelerate in the clockwise direction and begin rotating counterclockwise. Once the motor reached rated speed, the inrush current would subside and level out at the full load rated current. If an operator were to release the momentary contact reverse button, the spring return would return it to its normally open deactivated state. Note that the now closed R1 holding contact maintains the energized state of the R contactor coil. This means that the primary R contactor stays closed and the motor continues spinning in the counterclockwise direction. That's the point of the holding circuit. It maintains the last asserted state. The E-stop, stop, and overload function as previously discussed for an ordinary reversing motor starter. It should be noted that the simultaneous actuation of both forward and reverse would disable both modes. However, upon release of the two buttons, the state of whichever button was last actuated would be asserted. By using push-button interlocking, this reversing motor starter makes it possible to directly switch from forward to reverse and vice versa, bypassing the stop intermediary. As alluded, a plugging event is characterized by a current draw many times greater than that of even inrush, a phenomenon already characterized by an intense but brief surge. For this reason, contactors intended to plug a motor must be sufficiently rugged enough to handle this event. Additionally, repeatedly plugging a motor can cause overload elements to trip early due to the cumulative nature of heat. Finally, the nature of the driven load must be considered when plugging a motor. A sudden reversal of a load with a large inertia could easily snap a shaft or otherwise damage the system. We'll discuss anti-plugging circuits that prevent immediate reversal in a moment. For now, let's consider plugging a good thing. Not only does plugging a motor enable immediate reversal, it can also be used to our advantage to decelerate a motor. Note plugging can only be used to rapidly decelerate a moving motor, not lock it in place like a friction brake. Plugging, like DC injection, regenerative, or other dynamic methods we'll examine much later, can only decelerate a moving motor. Once the rotor stops moving, these dynamic methods don't work well, and mechanical means like friction brakes must be used to lock the shaft. Consider this motor starter that uses a rotational speed switch and plugging to rapidly decelerate the motor when stopped. Recall from the Switches in Electrically Controlled Systems lecture that a rotational speed switch is an electromechanical device affixed to a shaft that changes states when it reaches a predetermined rotational speed set value. For this application, this particular plugging switch is often called a zero speed switch, in that any rotational speed above 0 RPM actuates the switch to its opposite closed state. This particular motor starter is intended to run the motor in one direction only. However, notice the primary schematic uses paired contactors quite like a reversing starter. The forward F contactor is wired such that phase sequence as seen by the motor is L1, L2, and L3. The plug to stop P contactor is wired such that phase sequence as seen by the motor is L2, L1, L3. Since this motor starter is intended to be unidirectional, the plug to stop P contactor's only purpose is to decelerate the moving motor. Let's see how the ladder logic diagram incorporating the zero speed switch makes this happen.